Okay, so to continue with our um, nonlinear methods of solving roots, we now discuss the Newton's method or the Newton-Raphson method. This is also known as the Newton-Raphson technique. Okay, so the difference between the um, last method, the second method, or the linear interpolation method, is that I need 2 points in order to get a slope. Okay, I need 2 points to get at least a slope, and interpolate that into the x-axis by further extending the line uh, up or down. No? So if the two guess values are outside the root, no problem with the second method or the linear interpolation method. So is true with the Newton's method. But in the Newton's method, you also save a guess value. No, you only need one guess value, which is xo, and the next uh, value is already obtained by a simple equation given to be this one. Because we don't need a slope, 2 points to form a slope, simply get the tangent line, and we know for a fact that the derivative of a point on the curve represents the tangent to that curve. So we don't need another point just to define the slope, but rather just equate it to the derivative of the function itself. Okay, so this is simply f prime of x. Okay, so this is now my equation for the next guess value, x1. So I just plug it here. This is my functional equation or function. It's my slope. The derivative of fx is simply this one. Okay, and then on my first iterate, I simply start from zero. Actually, you can start uh, at a point wherein this is very easy to solve, for as long as this is near the vicinity, no, of the root. Okay, so what if this is not near the vicinity? Okay pa rin, no? It will converge, pero mas mabilis lang, of course, if it is near the vicinity of the root for faster convergence. Okay, so after that, we simply get the functional value at the first iterate, xo, and the slope at the first iterate, xo. Okay? Okay, so this is now x1 to be solved using the formula. Okay, so this is the formula. This is just a point slope form of the formula, no, in our algebra. So you get now the first value of your x1, which is 0.333. Let us check. Wala ata yung solution dito sa Whitley. Okay, so I forgot to write the solution here. So fx1 is 0.068418 in this case. Then second iterate, I just copy this and paste it here. So I get x1 to be 0.360171. Look at the convergence, it's very fast, no? So it jumped to a value very near the final value here on the fifth iterate of the linear interpolation technique. Okay, just on the second. And on the third, of course, it has the match, no, the efficiency and convergence of the secant method or the linear interpolative method. Okay, so at this point you can stop because the functional value here is almost zero, meaning to say you have approached the x-axis. Okay, your value of y is almost zero, or simply the function of x1 is almost zero only at the third iterate. So that's how Newton's method, or the Newton-Raphson method, fares with the other methods. So you can come up with some conclusion, maybe try to look into and to the method which is more accurate. Sometimes you don't need the fast converging methods or a very complicated interpolative expressions like the Mahler's parabolic interpolation. You only need efficient method and very simple parang mas madaling i-code, no? Simple coded procedures to fare well with other methods. Hindi mo naman kailangan yung mahihirap, no? And this Newton's method, Newton-Raphson, is not very difficult. That's why it's the most useful method kahit siguro sa mga engineering programs, no? Non-linear or linear man siya. Of course, linear, you don't need to solve for the derivative, no? Sa mga non-linear problems, the Newton-Raphson method is really very powerful and efficient. Okay? So that's it for the methods. So we'll discuss more the Mahler's method and the fixed point iteration method on the next video. Thank you for listening.